Although I wasn't born in the 1960s to 90s, I admire that era. I believe the period from the 60s to the 90s was the peak of technological development led by the United States and the Soviet Union. Starting from Sputnik, the Apollo program, and the rise of the personal computers, every scientist back then was deeply dedicated to creating new technology. It was a true race toward innovation. The reason I love that era is because the hardware is limited. At that time, hardware wasn't as powerful as you might expect. Just 1 megabyte of RAM was considered huge, and computers could only handle a single process at a time. Engineers had to make their software work within those tight limitations, which led to extreme levels of optimization. Some of the best examples of this can be seen in video games, especially Super Mario Bros. And Doom. Nintendo managed to develop a game where the memory size was actually smaller than a single screenshot of the game. And Doom is legendary for how perfectly its code was written, squeezing every bit of performance from the hardware. Following that same spirit, I decided to build my own LLM using a single GPU. At first, I aimed for a 1 billion parameter, but when I tried to pre-train it, I ran into out-of-memory errors, even with a batch size of 1, which is pretty impractical. On top of that, I didn't have access to a large enough dataset. So, I scaled down to 72 million parameters, but that felt too small. Eventually, I settled on a 150 million model. I'll go into the details of how I trained the model in future videos. In this one, I'll focus on the architecture I chose and why I choose it. I took inspiration from DeepSeek's latent attention mechanism and ROPE. Let me break down what that means. The attention mechanism was first introduced by Google. It was an astonishing idea that led to a boom in artificial intelligence. However, attention had one big problem. It was computationally inefficient. Its complexity was big O of n squared. To solve this, researchers came up with the latent attention mechanism. Unlike traditional attention, latent attention doesn't compute interactions between every token. Instead, it uses a fixed number of latent tokens, reducing the complexity to big O of n plus m. This allows for much more efficient computation, especially when the sequence is long. Rotary positional encoding, or ROPE, is a positional encoding technique. In the original Attention is All You Need paper, position embeddings were based on sine and cosine functions, giving each position a fixed encoding. ROPE adds a rotational component. With this additional encoding, attention can represent not just absolute patterns, but also relative positions between tokens. And I added Mixture of Experts, or MOE. MOE is made up of multiple smaller feed-forward networks. In simpler terms, each expert is like a separate mini artificial intelligence. During training, a gating network, which is also learnable, decides which expert should process each token. To avoid the model always choosing a single expert, I added a balanced loss to the gating network. This encourages more even usage across experts. Conceptually, this is how the Raptor model was built, and I pre-trained to predict the next token, fine-tuned as a chatbot with LoRa. You can use the model on the description below. I am now building an English version Raptor, so be tuned. Full code is on my GitHub, feel free to clone it. I'll see you in the next video.